Hello everyone, and you are welcome to the fourth session under Unit 1. And here we are going to look at thin layer chromatography. So at the end of the session, you should be able to separate two given substances using thin layer chromatography. Okay, so thin layer chromatography is an extremely useful technique for monitoring reactions. So mostly in monitoring a chemical reaction to know that probably your product has been formed. You can you started with um, starting material. So after the product is formed, you have two compounds present, just like the fluorine and the fluorinon. So when you run the TLC on the the reaction vessel using you run your TLC based on the content in the reaction vessel, and you realize that now two components have been formed, then you know that your product is being formed because you started with one compound. Now you can also use that for qualitative tests to know the number of components that are present in the complex, right? So you have a plant extract, you want to know the possible compounds present or the number of components that are present. Then you can use TLC to do that. So TLC uses a stationary phase, usually alumina or silica gel, and a mobile phase, which is usually organic solvent, right? So now the key point is that depending on the polarity of the components in the mixture you are trying to analyze, different compounds will travel at different distances, right? So these different distances will bring about the difference in the retardation factor that you calculate, right? So the more polar compounds will stick on the polar silica gel and travel short distance on the plate, whilst the non-polar solvents, the non-polar components will diffuse and then will travel at large distances, right? Okay, so in the analysis, so you find the retardation factor, which is a ratio of the distance traveled by the component to the distance traveled by the mobile phase, right? So the spot, in other words, you can see the spot distance over the solvent distance. So 2.1 over 2.8, giving you a value between 0 and 1, right? So we have 0.75. So you calculate this retardation factor for the individual spots on the TLC plate, right, to identify which is which. So in a case where you have an unknown compound, you are trying to find its the component, right? You have a mixture, you want to find the unknown, then you run your TLC, and then you run it together with a standard, then you compare their RF values, and then you say that this is a possible match. Okay, so before you run your samples, you can prepare the plates yourself. You can cut them into the sizes that will best suit the work you are going to do or the number of spots you want to to spot at a given time, right, or on the plate. And then of course you will go ahead to determine the solvent system you use. Now one thing you need to know is that the more polar solvent will move faster than the non-polar solvent if you use a polar solvent as the developing solvent, right? And similarly, if you use a non-polar solvent like pentane or hexane as your developing solvent, then the non-polar components in the mixture will elute faster than the polar solvent, the polar component. Okay, so for very good separation, there are also instances where we have to combine some polar solvents with non-polar solvents just to make sure we get a very good solvent for our separation. Because a good solvent system is one that is able to move all our components in that mixture from the baseline. So a good solvent should be able to pick the polar together with the non-polar solvents first. Then these are some of the examples. Okay, so to run your TLC. You first of all get your plates. You mark the places you'll be spotting, right? And you make sure they are spacious enough, just so you don't end up having some of the spots dissolving into the next spot. So you get your TLC chamber, you saturate it, or you add your desired solvent system into the TLC chamber, and then you add a filter paper to the chamber, and then you cover it. And the purpose of the filter paper is to saturate the chamber with your solvent system, right? Then you go ahead and then spot your components on the baseline. Then you run your TLC. So you let the solvent go about 90% up in TLC plate. So if this is TLC plate somewhere around here, should be okay. And then you remove your plate from the chamber. Mark the solvent front immediately, because if you don't do that, the solvent will evaporate and you won't see the solvent front. So you mark the solvent front. That's where the solvent got to as your solvent front, and then you do your calculations. So wherever your spot got to in the plate, you divide that over your solvent front, and then you calculate your RF factors, right? So there are cases where it's difficult to see your spots, then you use other techniques to do your visualizations, and you'll be looking at them shortly. So this is a typical visualization technique. Now in the visualization, right, there are two types of visualization TLC. You have the non-destructive technique, and then you have the destructive technique. Now the non-destructive technique means that you can do your visualization over and over again, and it has no effect on the plate. The TLC plate is not destroyed after the process, or your spots are not destroyed after the process. So a UV, using the UV lamp or putting your plate under UV lamp is a typical example of a non-destructive visualization technique, right? So it helps you identify your spots. So you realize that some of these spots may probably not be visible outside the UV lamp. So you use the UV lamp to help you identify them, and then you circle them before you calculate your RF, right? Then you have the destructive approach. So here, realize that this is iodine chamber. This is used to visualize the spots. At the end of the day, the spots are destroyed, the plate is destroyed, and you can't do anything anymore with the plate. So another thing is the fact that if you want to use the destructive visualization technique, you have to make sure you've done your UV lamp visualization before bringing it here, because the moment you put it in the iodine chamber, everything is distracted, right? So after using the iodine chamber, you can't bring this back to the UV lamp for visualization. However, the non-destructive visualization technique, which is the UV, can be used, and then we can bring our plates into the iodine chamber for the final visualization technique. So let's look at this practical example or experiment you did in the lab. Now you are going to extract pigments from tomato, papaya, and carrots, and then you are going to run TLC analysis on them to know the kind of extract you were able to remove from these plants. So we have beta carotene, alpha carotene. We also have xanthophyll. So these are all in tomato, papaya, and what our carrot. The process is, depending on which extract you are working with. As in you are working with the tomato, then you can use the tomato paste, or you can use the fresh ripe tomato fruit. So you add 3 ml of acetone to the paste, and you mix the oil with a spatula, and then you remove the spatula, and then you filter with a filter paper, right? But you have to make sure you do it slowly, just so you don't destroy the filter paper or tear it into pieces. So after going through this process and getting your your extract, right? You're going to concentrate that extract, and then you do a TLC analysis on the extract to get to know the number of spots present, right? So a different solvent system will be used in the process to remove the extract, the desired extract, and then this is basically everything about the process that you're going to use to get your extract from the papaya, the, the tomato paste, and then of course the carrot. So at the end of the day, you are going to run the TLC on the extracts you are able you got from the three plants, right? And then you're going to run the TLC. So in the TLC you mark 1, 2, 3, and then 1 will be for the tomato, 2 will be for the papaya, and 3 will be for the carrots. And then you run a TLC analysis on them. So handle them only. So you have to make sure that the TLC plate is only always handled at the edges. So you don't have to touch the surface of the plate. And then you make the 3 light marks at the base of the TLC plate, and then you draw your baseline, and because that is where you're going to add your samples. So afterwards, you do the same thing. You get a TLC chamber. You add your solvents. In this case, you're going to use 2% acetone in hexane. So you realize that this time around we are using a mixture of solvent. We are using a non-polar solvent together with a polar solvent, right, to do our elution, right. The spots should be as small as possible in order to minimize tailing. Now, tailing is the process where you end up having your samples or your complex not being separated, but just be traveling along the plate like that. So you don't actually see the number of components that are present. You want a very good separation. So you have to spot just small amount of the sample on your spots. Now, when the spots are dry, place the TLC plate in the developing chamber. Gently close the chamber. Now, be sure that the bottom edge of the TLC plate is in the solvent, but the spots are above the solvent. Yeah, this is basically to make sure that your solvents don't end up being dissolved in your spots don't end up being dissolved in the solvent, right? Because once your spots are dissolved, then there will be no elution. However, the solvent should come from below the spots and then pick the spots and travel the spots along the plate. So always make sure that your solvent is below your spots, right? Now, when the spots have moved to the solvent front, remove the plates, lay them on a clean surface, and allow them to dry, right? And then when they are dry, you can take them under the UV lamp and then view them. Now, when you put them under the UV lamp, you just have to make sure you circle where all the spots are showing quickly, and then you take it out of the UV lamp and calculate your RFs. Now, these are questions you need to address. Why is acetone used in this experiment? To give examples of other solvent that can be used in place of acetone. Now, acetone is a polar solvent, so for other solvents, I think we've looked at some examples. Now, why can beta-carotene and lycopene dissolve in hexane? Now, whenever we talk about hexane, we know that hexane is a non-polar solvent. So, if beta-carotene and lycopene dissolve in them, then you can attribute that fact to the fact that they are non-polar organic compounds. Now, are the pigments in tomato, papaya, and carrot the same or different? So, based on the TLC results, did you get the same number of spots for all 3, or you had 2 for 1, 3 for 1, or 1 for others? So that tells us that the components in these 3 plants are the same or different.